All right. So the topic we'll be discussing in today's lab is attention modules and transformers. Essentially, what ended up happening after a point was that CNNs didn't really perform very well on certain tasks, right? In the past lab, we saw sequence modeling, right, where we looked at taking a sentence and trying to like taking a few words of a sentence and trying to predict what the rest of the sentence would be, which is a machine translation, which is not exactly a machine translation task, but it's a predictive task for sequence data, right? Similarly, we could have other machine translation tasks where, let's say, I take a word in English and I want to convert it in. I take a sentence in English and I want to convert it into a sentence in French, right? In that situation, there are a few important things to remember, right? Like we saw in last lab, each word will need some sort of representation, right? Each letter or each word would require some sort of representation, and each word would have to have some semantic context, right? Take for example, I say that this box of chocolates is good, right? In this context, good needs to have a certain meaning to it, right? It could also be bad, right? Therefore, the semantic context could also have could be that this box of chocolates is bad, right? And it's therefore conversion to French would be done in a certain way. Um, Now, obviously, there are like absolute direct translation tools that can do this for you. But if you sort of want to make, um, if you want to make a tool that like sort of understands language semantically and wants to provide a representation, sequence modeling and machine translation tasks are sort of what is the norm for things like this, right? So we're going to start with something called an embedding. I'm just going to put up a photo on screen. Are you guys able to see my screen now? Is my screen visible? Hello? Guys, is my screen visible? Okay. So essentially what you can see here is that like certain words have meanings, right? So man is related to woman in a certain way, the same way king is related to queen, right? There is a relation between the genders here. Similarly, there is a verb relation, right? Walking, the past tense of walking is walked, and there similarly the past tense of swimming is swam. Now, in the last lab, if you remember, we used something called one-hot encoding, right? Where we took each letter and we simply represented it in a point in an n-dimensional. We simply represented it as a vector in an n-dimensional space, right? And each vector was unique and perpendicular to the other, right? As we had discussed, right? The dot product of each would be zero. Um, Now, the problem which sort of stems from something like that is that if I have 100 words, my dimensionality becomes 100, which is extremely large, and there is no relation between any of the letters or words, right? Walking is the same level of distance apart from walked as swimming is from walking, which is not something we really want, right? We want swimming and walking to be distinct things, but walking and walk to be similar, right? There has to be some sort of uh, semantic representation or some sort of understanding within the embeddings themselves, which allow us to sort of understand the difference between them while also representing them in a smaller space, right? Something and in something that a model can understand, right? So this is where word embeddings come into play. So word embeddings are essentially um, the representations, the vectorized representation of words into a smaller into a latent space or in a smaller dimension. Now, if you guys remember an encoder decoder network, which we have also discussed in the past, I'm also opening that up on screen right now. This is a bad image. Wait. Right. So as you can see here, there is like so this is an encoder decoder network, right? Where the first part of the network, which is the encoder, takes in like an input of a given size and is mapping it to a much smaller size, right? Now the point of an encoder network is to be able to represent or to try to represent all the information that is present in like the original feature vector into something that is smaller. So those of you who have done digital design as a course would be able to relate to what an encoder means, right? It's a literal concept um, in digital design where you take like I think a multiplexer and you sort of no wait you take an encoder. There is a literal device called an encoder where you take maybe 8 data lines and you encode them into 3 lines, right? Similarly, here you're taking an n-dimensional feature vector and linearly transforming it into a space which is smaller, but it's supposed to contain all the information inside, right? This is what the encoder part of the network does. And similarly, the decoder will take this entire like small set and try to replicate the exact same vector as the input vector, which is to say that it is supposed to map out the same sort of features that were present in the input vector. Now, here what's exactly happening is that if we have to, let's say, represent a word in a smaller space, right? We'll have to have some sort of input word, right? And we'll probably do that using one-hot encoded vectors. And each one-hot encoded vector will go through an encoder, get mapped to a latent space, and then that latent space representation will be mapped to an output. Now, models like now there are certain types of models which have been used to vectorize words, right? This process is going to be called vectorization, where I take a word and I vectorize it into a smaller dimension or into a smaller space. Um, and a lot of this has to do with unsupervised learning, right? Because there is no real correct answer for vectorization. You can use different types of vectorizations, and they would all give you similar results if you use the same technique, right? But it's not a deterministic algorithm. It is in some senses stochastic. Um, but why these representations are important is that coming back to the original slide, right? When I take, let's say, man, if I take the feature embedding for man and I add woman to it and subtract king, or I take king, add woman, and subtract man, it would actually give me a representation which is very similar to queen. So this is sort of the beauty of why we use embeddings like these or representations like these instead of using something which is like a one-hot encoded vector, because something like a king plus woman minus man will actually give me some very a representation which is very very close to the feature vector for queen. So this is a little bit about embeddings that I wanted to discuss with you before we move forward. Um, what we'll be discussing next, and I hope this is clear to everyone because this is a very brief explanation. It's not a very in-depth explanation. There are a lot of things that go into the process of creating these feature embeddings or these word embeddings. Like if you'd like, you could go through some like a word to vec model or a glove embedding model, and those things get very complicated very quickly. So this is just a very brief intro to what word embeddings look like, because at least for the scope of this lab today, we'll only be considering like pre-made word embeddings, and we won't really be looking into how these embeddings were made. But if you'd like, I can share some resources on what you could read there. So next, what we'd be looking at is probably one of the most important papers with regards to the evolution of deep learning that has taken place. Let me just share my screen once more. And it was a paper called "Attention is All You Need." Right. So we've seen what. Now, this is not my presentation, as you can see. Um, and sort of the point is that after CNN sort of hit a point, right, where you couldn't really optimize them further to achieve similar types of tasks. And certain tasks were simply not like easily possible with CNNs. We built a recurrent network last time, and even that wasn't a very good solution. Obviously, we didn't do it on a very large data set, but if you go through literature and you look at the results that like recurrent networks had come up with, they're not great. And it's very difficult for a recurrent network to sort of understand semantic um, context very well, right? Because after a point, it just becomes um, about the past input and the current input. There's very little to do with either the next set of inputs in the sentence, because it mostly doesn't see those, or the previous few inputs before the before the like the exact last word, right? Um, so this is all pertaining to last week's lab, which I'm hoping you're all familiar with. So that's sort of a problem with recurrent networks. It's even worse for machine translation tasks. And let me pull up something on a machine translation task so that it's better for you to understand. So, like the example I had given earlier, right? You could convert something like "How is your day" to a French sentence, right? Here, so they've written LSTM here, at least for this image, but you can sort of ignore the LSTM here. And just try to understand that what they're trying to do here is they're converting each word in the sentence to some sort of representation, and they're encoding it to a state which they're then decoding into this French sentence, right? So this is an encoder decoder architecture similar to the CNN architecture I had shown you just now. Except here they will be encoding each word. It's The sentence will be encoded together, and each word will have some sort of semantic context in the sentence, which is important for that word, right? um, if "how" is not given the same sort of a semantic context as the rest of the sentence, "how" could, in for the machine at least, could also be equally likely, with equal likelihood, be replaced with like a "why is your day" instead of "how is your day." While "why is your day" is not what you wanted to ask, or not the answer you wanted in French. So that's sort of the problem with machine translation tasks, right? Each word needs a certain amount of context or some sort of probabilistic value attached to it, which is, if you think about it, very similar to how we pay attention to things, right? If I want to encode "how," the word "how," I should probably pay more attention to the word "how," but also pay some attention to the rest of the words, right? So this is sort of what researchers, I think at Google, I'm not sure who published "Attention is all you need." Um, but this is sort of the context with which they sort of came up with the idea of um, they came up with the idea of attention and self-attention, right? Which essentially led to an entire new field of deep learning being created, which is called transformers. And transformers outperformed CNNs on nearly every task by a mile. They beat them by a mile. It's not even close, right? So attention, as you can see, was to solve machine translation and sequence transduction problems similar to what I just showed you. And self-attention is this, right, where each element is going to pay attention to every other element, and the word that we're looking for immediately is going to have a higher can have a higher value depending on how it's been trained, right? um and different positions of the same sequence will have to be used, or will have certain weights attached to them to compute a representation of the same sequence. This sentence doesn't make a lot of sense right now because it's a little weird, but I will show you another image which I hope will make more sense. So, what essentially ends up happening, right, is that each of these, I think they have an, no, they don't. Right. So each of these like vectors, or each of these words can be will be used as three things, right? Each of them will be used as a key, a query, and a value. The query vector or the query matrix is what we'll be using across all attention heads at a given point in time. Actually, just give me a second. Right. Sorry about that. Right. So this is the image I wanted to show you. So if you look at this image closely, you can see that each word. Okay, so x1, x2, x3, and x4 are words in a sentence, right? Think about this as words in English, and y1, y2, y3, and y4 are words in French. The task at hand is to convert an English sentence to a French sentence, similar to what we had done earlier, right? Uh, this is what an attention block looks like. This is multiplication, where you take in a weight of w1 and you multiply it with like an x1, which is your vector. Each of these are representations of the English of a word in the English language in a vectorized format, similar to the embeddings we had just discussed, right? Um, I hope this is clear until now. Okay. So if you think about it, this is the word that I'm going to be producing right now. So for y2, I will have x2, right? Because I will have to have corresponding words. And if you notice, this is a common vector or a common word which is being like placed in every single part of these attention blocks, which means that this is the value being queried, right? This is the question about the word that we're asking. Does this word belong here, as much as like how similar is this word to x1? Should this word be here because x1 is just before it, or should this word be here because x1 is present in the sentence, right? These are important questions that need to be asked with the word x2, and this is exactly what the query key is doing, right? X2 is the query key which is asking whether or not they should be placed here. Similarly, sec. Similarly, these values, the values that you can see right just up here, right? These are the values. Like this is literally the value matrix that is called, right? Where each of these vectors, x1, x2, x3, and x4, at their respective like positions, x, which is 1, 2, 3, and 4, will be multiplied with x2 to produce a weight matrix. Why is this important? Because this is sort of checking how similar x1 and x2 are, right? With the query key, how similar is this value with the query key, so that it should whether and it discusses whether or not um like with what weightage x1 should be present as part of y. Oh, sorry, x1 should have some weightage with regards to the presence of y or x2 and y2, or how should y2 be created, right? If you go back to how we discussed neural networks, the this essentially forms like this forms a weight matrix, because these will be dot product together, to form a weight matrix, which will then be multiplied with x1, which in turn will be added together. Each of these four weight matrices times their respective key matrices will be added together to form y2, right? So these weight matrices are very important. And as you'll see shortly, they form a learnable parameter, because right now x1 and x1 till x4, all these vectors are deterministic, right? All these are embedded representations of a word. So what are really the learnable parameters here? What do I put in a neural network so that something changes, right? So far, nothing. But we'll see that x1, this matrix, which is the value matrix, is not just x1. It's x1 times another weight matrix, which in turn will form a value matrix. Um, Now this is relatively confusing. Does anybody have any questions up until this point? I will be explaining attention again through this diagram. Okay, seeing none, I will just go through the concept of attention again, right? So what we're doing here is we're weighing the relative probability or the relative position of x2 with regards to its surrounding words, right? And we're doing that by having x2 as a query key, x1, x2, x3, and x4 as value keys, which we're multiplying together to form a weight matrix. The weight matrix is being multiplied with the key matrix here, which is also x1, x1, x2, x3, and x4, to see where to see with what value or with what weightage x each of these matrices should be added together to form y2. This is the concept of attention. The value of x2, or the relative amount of x2 that should be present in y2 with context to its surrounding matrices and its surrounding neighbors, right? Now, as I had mentioned previously, these are not a lot of learnable parameters, but you need some learnable parameters, right? So how do you really go ahead and create learnable parameters here? So as we had discussed, query key and value matrices will be present, and uh, the idea is to select a value referenced by a key, as we had seen, relevant to a query, as to what we're trying to pull from input, or what is the value assigned, or what is the question we're asking to about a word, right, with regards to its actual values, right? And keys and values are word embeddings, not words. So a mapping a query which is from the paper, the original paper, attention is all you need, where all of these queries, keys, and values and its output are all vectors, and the output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key, which is a little bit of like which is a little complicated way of explaining that you're asking a question about a given word with respect to its position, and the position and its surrounding word is represented by the value matrix. So how really do you compute this attention, right? So as we had seen, the query and the key matrices get multiplied together. um, and here the attention function that they've come up with is taking a softmax activation over the matrix product of query and key matrices, and then multiplying it with the value matrix, right? um, so this forms the softmax of these of the product of these matrices, form the from the weight matrix, as we had seen earlier, which is then further multiplied by the value matrix to form the and all of them are then added together to form the net output y, right? Very similar to what we had seen in the previous image. Now, query key and value all should represent the same representation, right? Because they're all the same word embedding. But they're not really, because query key and value matrices are essentially the same word embedding multiplied by a larger weight matrix. So I would advise you to do this on paper, but like a weight matrix n by n multiplied by an n by 1 matrix will result in another n by 1 matrix, right? Pretty straightforward matrix algebra. um and when you sort of think about it, the weight matrix has to represent the weightage of each part of the eventual feature matrix, right? And that's essentially what our learnable parameters become. After this, it's simply the concept of you could actually just take this and put it in a convolutional neural network or a standard neural network, and it works that way. Attention is a concept that was also applied to neural networks. But we want to see where attention really comes into use for transformers. Before that, we look at something called multi-head attention, right? So what we've looked at so far is like single-head attention or self-attention, where we've only looked at how much a single output sequence could be represented by with regards to a single input sequence. But what happens when I want to focus on different parts of the sentence at the same time, right? So you take multiple attention blocks and you stack them together and then you concatenate them. So this concatenation function could vary. It could be as straightforward as adding them and convert and mapping it to the space as is needed, or it could be a little more complicated, which I'm not very familiar with myself, but it literature exists. You could read through that if you'd like. So this is a little complicated, but I will just give you a brief explanation as to what they mean by positional encoding, right? Previously, I had discussed that the position of a word is relevant to its surroundings, but that also means that it needs to know where it is, right? The matrices themselves don't represent what position of the word they're at, what position they are in the sentence. So you can sort of use another vector or another value to represent where they are in the sentence. That's all a positional encoding is. And they've used these functions to represent it. Now, this is what a transformer architecture is, which is a little scary at first, but not as complicated as it may seem. So as we had discussed previously, this is an encoder network. The left side, like to the left, I can actually use a marker on this. So to the left of this line is the encoder architecture, right? Which is going to create embeddings and probability distributions for an input sequence. That's essentially the point of attention, right? That's why you don't use a standard encoder decoder network, because a standard encoder decoder network cannot create a probabilistic distribution of an input sequence, while an attentional sequence or an attentional encoder will be able to do that. That's literally the point of attention, to create a probabilistic representation of a given input sequence. So you take an input embedding, right, which is what we saw. You take positional encoding, which we saw is like the relevant position of a given of a given embedding. Here they've applied multi-head attention, and you can sort of see something similar to a skip connection here, like a residual. Like this is a residual connection, a skip connection, which sort of says that, like, if you don't want to go through multi-head attention, so this part addition is a concatenation of both the results of multi-head attention and the actual input sequence itself, right? This is what a residual connection looks like. I'm not sure if this was covered in the computer vision problems lab, but this is something that was covered in the ResNet architecture, right? Which is a very, very famous deep learning architecture. CNN, it was initially a CNN. It is a CNN architecture. But skip connections and residual connections are essentially form a part of that. And layer normalization, which is again a little complicated. We won't go into it this lab. We'll go into it when we discuss GANs. Right, here is a feed forward network, very similar to what we've done before, standard neural network. And each output embedding is then placed again into another set of multi-head attention addition normalization networks. And the next set of outputs is also given weightage, right? As you can see, the output embeddings are also placed into it, where and eventually after going through this entire set and a softmax activation, you get an output probability. Why is softmax activation important? As we had discussed in again last week's lab, I think, a softmax activation will give you the probability representation of a given sequence, or it will actually normalize the probabilities for you between 0 to 1, which is what you need. uh, a linear model will not give you good accuracy because it's a very large distribution, and your error um, optimization sometimes goes haywire. So softmax gives you the requisite sort of probability distribution that you need. um so this is essentially what a transformer architecture looks like, right? After this, the paper only talks about implementation and training details, but this is relatively heavy. So if anyone has any questions, you could ask them now. Okay, seeing none. Just an additional thing I wanted to add. There is something called masked or decoder self attention in brackets masked, right? This is essentially to say that if you are accepting output embeddings, you cannot accept the output embedding of the word you want to output, or the word whose output embedding you want to create, because that's looking at the answer and then like then answering the question. It's cheating essentially, which you don't want to happen, right? Because your model is now learning from the output instead of learning how to map the input to the output, which you don't want. So this is why you add masked self attention, where you sort of mask the output you want and some of the future outputs as well, even though you have them, right? Because this is a supervised learning task at the end of the day. um so that's about it with regards to the theory. um Again, open for questions if you have any. If not, we can start with the code implementation of transformer models right now. Okay, so we will start with coding it out. As with every, right. So you could go to something. So I'm not sure how many of you are familiar with a website called Hugging Face. But it's a very nice website that sort of allows you to use a lot of models that have been pre-trained. So like they've created tasks, right? So like image classification is a task. So they'll show you models that have been used for image classification um, and their accuracies on certain data sets, pre-trained values, pre-trained weights for each model. I think you can get a lot of models here. Um, so this is a very good website if you want to do something like that. They also have a very vast set of data sets which you can download directly from here, or you could like find their link to the GitHub and then sort of download it from there. But this is a good website if you want to explore a lot of different models, and I think it also gives you benchmarks for different tasks. So does another website called Papers with Code. So you could also check that out, where you have multiple data sets, and on each data set you sort of have um, a state of the art the state of the art models, right? So let's say ImageNet is the data set I want to look at. It will show me the benchmarks for each. It'll show me the benchmarks like this may be the best model, right? So it will sort of show me that, right? So coming back to the lab. So Hugging Face has a sample data set for transformers, which we'll be using. Git LFS is also, so I don't remember the full form of Git LFS, but if I remember correctly, a lot of large data sets on GitHub aren't stored as like sharded memory locations, um, which is similar to how you store things on Drive, right? Because they're very, very large data sets. So if I remember correctly, this sort of creates a memory location that points to the same data set every time, and you can use that. Let me just look that up actually. Yeah, so GitHub large file storage, which um, like points to the memory location where the original dataset was stored. So again, a lot of good APIs have been written, which it generates all the splits you need, right? You don't have to do any of the data loader work yourself anymore. So we won't be using the unsupervised split here because the task we'll be doing is supervised. But I don't see why it hasn't been completed. But anyway, yeah, we won't be needing it any that large set. Okay, so it's completed. So as you can see, it has a the features present are the text and the label associated to it, right? So we'll sort of see what the dataset looks like in a little bit. Uh, Again, we'll be using a small set of this data, and the reason is that we can sort of overfit what the data we have and see whether our model works or not, right? So a good way of checking whether your model is working is to overfit a very small section of your data on it instead of having to go through like the entire training process multiple times and to make sure that um, all your hyperparameters are in order. So it's a lot easier for you to overfit it a few times and see how well it works. And more likely than not, it's a good indication of whether or not your model is working. That's again something we'll be doing today. So again, as I had discussed previously, we'll be using word embeddings for each word, right? There'll be a vectorized representation for each word, and the fact that these representations are created by some unsupervised learning tasks, right? So Google came up with a model called BERT, which I think was one of the first transformer, not one of the first, but a pretty good model-based architecture, transformer-based architecture to create word embeddings, right? I think it has a very nice story attached to it as well about how the Google team was forced to come up with it in like a month or something. You can go through that if you'd like. But we'll be using one of the more modern versions of I think BERT. And these are all available online, right? So you don't really have to do the whole process of doing the word embeddings yourself. And more likely than not, you won't have a large enough data set for you to actually be able to do the whole set of embeddings yourself. So dot map essentially um, like returns each word after applying a function to it. So here we've like defined a preprocess function which returns a tokenized value of the example text that we're sending across, and it truncates it. Um, and it's going to apply this function to each part of or to each vectorized to each word, and it'll return it back to tokenized train set. Um, Transformers. Right. So Hugging Face also has a lot of documentation for data collation, right? So data collators mostly just help build batches, um, and again may apply some sort of padding like processes. Padding in this case very similar to the sort of padding we created for CNN architectures here, except you'll be applying it to mostly linear vectors. But a lot of different data collators you can use. We've used one with padding because it's a good collator. Um, you can go through different like sorts of collators and see what fits your task best, right? Let's say you're building a sequence to sequence model. Probably better off using this one because it's a pre-made one for that exact um, task, right? Uh, Similarly, you could use a variety of different things. Hugging Face has a very good set of documentation which you could use for this. Add in some text here. Wait. Model plus training. Right? So we'll be using a pre-trained model because transformers are pretty large in terms of, and we don't really have the kind of data set capability or computational capability to be able to train one from scratch. There are mobile versions of um, transformers available now. Something like mobile vision transformers are getting decently popular now, but even those are pretty hefty to be trained. They're not as straightforward in terms of training processes because you could apply a lot of different training techniques to it, and still it wouldn't give you the sort of results that um, the paper that it's been made in, the paper that it references, the paper that references it sort of like gives you, right? Uh, training tricks are pretty vast now. So we'll be using something called a distill bird model. Again, a very similar to, it's based on a bird architecture. Okay, so now we'll just write some code to report metrics. F1 score accuracy. So F1 score is, I think, the inverse of the harmonic mean, or the harmonic mean of precision and recall. For those of you who are familiar with the, it's like, what is the matrix called? Confusion matrix. So you have things like true positives, false negatives, and true negatives, right? And F1 score is the inverse of the harmonic mean of precision and recall, which is let me just check what precision and recall are, right? Yeah, precision is the number of true positives over all positive outcomes. Recall is the number of true positives divided by the number of true positives and false negatives. So you can like think about what precision and recall really means. Precision is how many true positives I got out of all predicted positives, and recall is how many true positives did I get out of all the correct answers, which is how many true positives I have predicted and the number of false negatives I have predicted. False negatives are also correct answers. True negatives are wrong answers, and false positives. Sorry, false positives and false negatives are wrong answers, right? So sort of think about what F1 score means. It's a metric for understanding how good your model is performing, and a high F1 score is a good thing. So logits are essentially the log of the corresponding odds, right? Um, the answers that you are getting right after while underscore pred are the log values of log of p of 1 minus p divided by 1 minus p, where p is the probability of that word being the correct answer for the of with context of the with context of the machine translation task that we had discussed earlier. So this allows you to actually access the Hugging Face. Wait, I haven't done it yet. Let me show you. Let me just log into this. This is going to take a second. My tokens page is not opening. Okay, never mind. Don't need to, as long as login is successful, right? So we'll be setting, yeah. So what we'll do here is that we'll create, not here. So generally when we're doing tasks that are like larger, and sometimes we don't really know how our model is like going to do, or the machine that we're doing training on, right? Sometimes it sort of crashes in between because of like how computationally complex it's getting, or just in general bad luck, right? So a good idea to generally um, work with is to save your model parameters. uh, it's done by creating a checkpoint, which makes sense, right? In a video game you create a checkpoint so that you don't lose your progress. Here you create a checkpoint so that you don't lose your model's training progress. So here we'll create let me we're keeping our learning rate pretty small, so we'll create um, per device. We only have one device here, which is one GPU. But we could have multiple. And another interesting thing about attention is that it can be parallelized pretty easily. It can be parallelized pretty well, which is why transformers can sometimes be trained or have faster inference times depending on your device, as compared to certain CNN architectures, which uh, are slightly harder to parallelize. That's not always the case, as was like explained in the AlexNet paper. They used two. It was one of the first papers to use two GPUs to train their model. Let's see what the error, what the warning here is. Okay, let's see what happens. Don't know what the error is yet. Okay, this is concerning. Wait. Let's see. So let me just show you what the error was, right? Um, so what was happening was that I had created a token on Hugging Face, which was for read, which means that I can only read previous models. I can't write, which means that I can't save anything that I've created. Um, Now that I've created a new token, which not this one, and I copy it, this error should resolve. But um, let's see. So the reason why we're doing this, right, this Hugging Face import login, is that we can use Hugging Face as sort of an area where we can store. It's already loaded. Oh, right. So it'll clone. It'll be able to store a lot of things that you've put up, right? So it has a lot of pre-trained weights already on it, which you can download. It you can also store your weights on it. So that's sort of the point of using Hugging Face because it's a very nice website, at least for our purposes. And trainer.train literally does your work for you. It's so cute because we've been using code which will at least been 40 lines or so, and that's what we needed to train a model, and this does it in a single line. So it's a nice API call, and you can actually change a lot of things, right? So as we've discussed, I think in the second lab, you can have different gradient accumulation steps, and you can change all of these things on just this thing, this 8-9 line code, right? Um, and will do everything which you need for you. As you can see, a lot of parameters. So it's a massive model, which is why we can't train it from scratch because it's not possible for us to train it on our system. Uh, I don't think even with Colab Pro it's going to be done in a relatively fast scenario. So I'll just write the code for the next couple. cells by the time this is done. So this should take about 4 or 5 minutes. Um, I think we should just done one epoch. Maybe 0.5 epoch. Yeah, this is gonna take a while. So instead, I think what we'll do is we'll change this and we'll make this larger. See how large we can make this without our system crashing. Yeah, I'm just gonna overfit on 300 samples or so because otherwise this is going to take a while. Runtime crashed. So what ended up happening was that something similar to what took place, I think, in a previous lab. Someone had pointed it out, where because we're using 64, um, a batch size of 64, which is 64 uh, samples per batch, it takes up all of our RAM, and because we're not using Colab Pro, we can't really use that much RAM. Um, so our system crashed, right? So we'll have to restart the notebook. Shouldn't take that long. That'll be quick. And now we'll change batch size back to 16 so that it does not crash out on us. And hopefully this is faster. If it's not, I think you just have to trust me that it works, and hopefully by the time you're done with today's test, it will be done training. Uh, Not a lot of code left after this. It's just evaluate. We'll push it to the hub. just to make sure we don't lose it. Okay, so not bad. It is training. It's taking longer than I expected it to. Okay. So yeah, this is taking a while. Um, so I've done this. I've tried this out before, and I'm pretty sure that it works. It will also be shared with you in the lab sheet with sample outputs as well. You can try out a few different outputs. So yeah, as you can see, this is one set of like inputs and outputs you can sort of have. Um, just to like explain what's happening here. Um, Once we've uploaded this online, right, our model, which is being done by this function, push to hub, right? Um, then you sort of have to download the model again from your own link. So I'll go to Hugging Face and show you the tutorial on how to do that again. But essentially, you're downloading your own model weights, your model weights again, weights, and using a pipeline to pass inputs and test it, right? And by other inputs as well. You'll get two things. You'll get an accuracy and you'll get an F1 score if I'm not wrong. Right. So this is taking a while. Until then, I think yeah, I'll give you a tutorial on Hugging Face. So essentially, what you'll be doing, right? So once you come here to this point, right, where you're having notebook login, this is common across both Colab and Jupyter. So if you're doing this on a local system and not on Colab, this will still work as long as you have a functioning functioning internet connection. So you essentially just need to create a profile on Hugging Face. Go to access tokens, create an access token. So you create a new token. If you do read, you will only be able to download models, right? Similar to what we had done here, what we have done here, where you're taking pre-trained weights and you're downloading them. If you want to upload models like we're doing here, where you have an output directory on your Hugging Face page, you need to be you need to have changed your access token to write. If you don't do this, it will not work. We had an error earlier because I made the mistake of having the read token instead of the write token. Once you've done with that, just copy the token and paste it there. You will be able to see your models, the ones you have put up in your in your libraries. You will be able to see any new data sets if you have any and you want to upload them. And similarly, you can like download a lot of other either data sets. You can download other models, pre-trained and not and pre-trained and otherwise. You can use like their API. So trainer.train is pretty fast, right? It's not fast, but it's pretty easy to use. So you can use any of these models and just directly um, hit it with trainer.train, and you don't have to write any more code. So it's a pretty lazy way of doing things, but it works well, right? So why not? So with that, we're pretty much done with today's lab.